Test. Okay, let's get started. We're running a little behind, it's fine. And we'll just see how fast we get through these problems. And yeah, so after we get through these problems, then we'll, I guess that's it. So I have 7 problems here. I guess if we need any more, we can jump into some other problems. But I think 6 of these you guys haven't seen before, which is nice because so these are also from previous midterms. And then one of them is a previous final problem that I just wanted to talk about. So that sounds good with everyone. All right, so I'm recording this, it's being streamed right now. It'll be up tonight. And then yesterday's was already up, and anything else? I think that's about it. So we're used to this now. Thanks for coming back again, for those of you that were here yesterday. And yeah, let's just jump into it. So problem 1 is going to be the following. This is from a 2015 midterm. And it's a really simple problem. Well, I think it's simple. You guys should find this simple now, but you got a equals 5, 3, 5 like this, which zeros everywhere else, and the problem wording says find an invertible 3 by 3 matrix C such that C inverse AC is diagonal. All right, so that's all this problem is. Okay, and so what's the idea behind this problem? What do we need to do? Anyone? Yeah, find eigenvalues and eigenvectors. This essentially, this problem, so don't be confused, right, by the notation or the wording of this problem, right? CAC inverse is diagonal. This just means that you want to find some matrix C such that you can write it as CAC is equal to D, right? Because remember, when we're diagonalizing a matrix, D is our diagonal matrix. And then if you just arrange some terms around, right, you get A is equal to C, D, C inverse. And that looks a lot like SDS inverse. In fact, it is. We're just calling that matrix with your eigenvectors in it a different name. So we're just calling it C. So whenever you see something like something inverse A something, and then you have like a diagonal or something dealing with diagonal in it, you're finding eigenvalues, eigenvectors. So, all right, how do you do this? Well, characteristic polynomial, determinant A minus lambda I is equal to, and that's going to be a determinant negative lambda, we got a 3 minus lambda, negative lambda, 5, 5, and then zeros. Okay. What's the quick way to find this determinant? Best way to find this determinant. There's one right answer. Cofactor where? Yeah, middle row, middle column, right? So we'll place that in. Okay. And so what is this? This is equal to 3 minus lambda, because that's the row we targeted. All right. And since we're in the second row, second column, we have this -1 to the 1 plus 1 term, or whoops, 2 plus 2 term, right? And that comes from the fact that we're in row 2, column 2. And then we have the determinant of everything left over, lambda 5, 5, negative lambda. Okay? And that's equal to 3 minus lambda. All right, -1 to the 2 plus 2, that's just 1, so we can ignore it. And then this determinant here, this is lambda squared minus 25. All right, so again, this problem works out where your characteristic polynomial isn't that terrible, right? It's pretty easy to factor this, but that's not always going to be the case. Your characteristic polynomial is not always going to be this nice. So I think on the practice problems, there is an example where the characteristic polynomial isn't easily factored. You need to know how to factor cubics. I've said that 3 times. So don't have that happen to you. So okay, so you have this. Now we factor lambda minus 5, lambda plus 5, right? Good enough. Set this equal to 0. All right, and now we recover our eigenvalues, which is lambda is equal to 3, 5, and -5. Okay, the next step is to find the eigenvectors. So let's do lambda equals 3. And so we need a minus 3i. What is that equal to? Okay, so we just look at this matrix here and we subtract 3 off the diagonal, right? Or let lambda equal 3. And so we get -3, 0, 5, 0, 0, 0, 5, 0, -3. Okay, and remember, solving for eigenvectors, our right-hand side, we're essentially solving this augmented matrix, right? And so this is one of those examples where you should be able to eyeball what this eigenvector is going to be. So can anyone give me a possible eigenvector here? Yeah.
1, 1, and 3/5.
Okay, sure. That wasn't the one I really wanted, but I guess that one works. There's one that works a lot better that doesn't have fractions in it yet. Yeah, 0, 1, 0, right? Because if I multiply this matrix by 0, 1, 0, that just takes the second column. Okay, so we want 0, 1, 0. And so here, let's just say V1 is equal to 0, 1, 0. Okay, and one quick side note here that doesn't really have to deal with this problem. This V1 here, that I'm just numbering my eigenvectors, okay? That it doesn't have to deal with like what the eigenvalue is. So I know sometimes there's confusion if like lambda was like 1, 2, 3, and then I call these guys V1, V2, V3, right? That's just pure coincidence there. V1 just means this is my first eigenvector that I found. Okay, it has nothing. This subscript has nothing to do with what the eigenvalue is. So, okay, that's V1. There's my eigenvalue, eigenvector, and for lambda equals 3. So second one is lambda equals 5. Okay, so now a minus 5i, what is that equal to? -5, 0, 5, 0, -2, 5. Should be -2, right? Okay. I'm mistaken here. This is fine. And then 5, 0, -5. Okay, same idea as before. Why don't we try to eyeball this eigenvector as well? So V2. All right. And what can we do? What can we do here to get an eigenvector? And it is, yeah.
1, 0, 1.
1, 0, 1. How'd you get that?
The first one is -5 and 0 and 5, so those cancel. And then
Right.
The second one's only 0.
Right. This one's 0, right? So if you have 1, 0, 1, the middle 0 cancels this 2, right? And and then these zeros cancel with ones, right? So yeah, so 1, 0, 1 works. Yeah, and the idea is just try to fit something for one row, and then adjust accordingly. So if you tried 1, 0, 1 up here, right, you realize, hey, 1, 0, 1 works here, and it also works here, and it also works down here, and then you're done, right? So there was no need to do any like row reducing or like finding, you know, linearly, like using free variables and stuff like that. Okay, so I mean, and it's always good to check, but 1, 0, 1 is definitely my preferred choice there. And again, it doesn't have to be 1, 0, 1. If for some reason you want to put 2, 0, 2, like go for it. Okay, there's nothing stopping you from doing that. The reason why it's okay to choose any eigenvector that you want is because these eigenvectors end up going into C, right, and C inverse. Okay, so essentially, when you invert like the 2, 0, 2, it like cancels the fact that you multiplied it by 2. All right, that's a really hand-wavy explanation, but that's kind of why we can choose any eigenvector we want, and it doesn't just have to be 1, 0, 1. So yeah, so 1, 0, 1, that one's the simplest one, so we'll stick with that one. And then lastly, lambda equals -5. Okay, so what do I have here? Now I have 5, 0, 5, 0, 3, 0, 5, 0, 5. Yeah.
Isn't it 0, 8, 0?
Oh, 8. Yeah, you're right. I mean, it doesn't matter. Like, that's the one computation mistake you can make on this problem. Because what's going to be my eigenvector? Yeah.
1, 0, -1.
Yeah, 1, 0, -1. That works well. You can do -1, 0, 1. It doesn't matter because that's just a scalar multiple of this one. And all right, so we got my 3 eigenvectors. Okay. Any questions up to here? All right, good. And so now what do we do? Now we need to form C and we need to form D. Well, I guess this problem doesn't actually require you to form the D matrix, right? Because it's only asking you to find an invertible 3 by 3, right? And so you only need to find C, but for the heck of it, let's find D. So for D, I'll let that be 3, 5, -5, right? With zeros everywhere else because it's my diagonal matrix. Okay, and then C, right? In the first column of C, I have the eigenvalue corresponding to 3. So that needs to go there, or the eigenvector, which is this guy, 0, 1, 0. And then in the second column, I need the eigenvector corresponding to 5, which is 1, 0, 1. And then in the third column, I need the eigenvector corresponding to -5. So that's 1, 0, -1. And so here's my C, and you're done. Yeah?
So if we were to need to construct a basis for the eigenspace, is there a case where the vectors that you get won't automatically be linearly independent?
Yes, that comes when we have that defect, like when we haven't talked about it in class, so you don't have to worry about it for this midterm, but that happens when the matrix is defective, right? So remember, I talked about it briefly yesterday, when that means when you have a repeated eigenvector or repeated eigenvalue, but then A minus lambda I, the nullity of that, is not equal to the amount of times that eigenvalue is repeated. That's when you get into that problem. So, but for the purpose of this exam, you only have to be able to identify when it is defective, or so defective is not diagonalizable, but you don't actually have to like deal with the consequences of it being defective. Okay? So you just need to be able to identify it. Any other questions? No, pretty routine, right? So you'll see something like this on the exam, I'm pretty sure. These show up like every midterm. Okay. Let's move on. Where to put my sheets? There. All right, let's talk about, so here's the previous final problem that I want to talk about. It's a really nice one where if you know what you're doing, it takes you like 15 seconds. If you don't know what you're doing, it'll take you like 10 minutes. So number 2, here, this is from spring 2016, and it's the following problem. Find a 2x2 matrix whose eigenvalues are lambda 1 is equal to 1, lambda 2 is equal to 6, and the corresponding eigenvectors are v1 is equal to 1, negative 1, and v2 is equal to 4, 1. Okay, so how do we approach this kind of problem? Well, let's take a look at the information that we're given. What do we have?
Eigenvalues and eigenvectors.
Yeah, we have eigenvalues and eigenvectors, okay? So we need to find a matrix that has these eigenvalues and eigenvectors, okay? One way we can do it is we can just brute force a bunch of matrices until like one of these shows up. Yeah.
You use A equals STS.
Exactly. That's the point of this problem. Is you want to use the fact that any matrix A can be written as SDS inverse. Right? And how will we know to do that? Well, we're given eigenvalues, right? And so how do eigenvalues relate to a matrix? Well, they're on the diagonal, right, of a diagonal matrix. And then you're given eigenvectors, and you know that for eigenvectors, we can put them into a square matrix that's invertible, right? So we use this fact, A is equal to SDS inverse. So what should my S be? Yeah.
Vector 1, vector 2, so 1 for negative 1, 1.
Yeah, exactly. So you just put vector 1 in the column, vector 2 in the column. Well, okay, so I did this kind of backwards from what I usually say. I usually say make the D matrix first, right? Because the diagonal matrix tells you where to put your vectors. Well, that's fine, because now, since 1, negative 1 is here, well, 1, negative 1 goes with lambda equals 1, so I need to put lambda equals 1 in the first column. And then for D, we put, right, 6, and that's because it's the second matrix. It's the second column vector there. Okay, so now the only really annoying part of this problem is to find S inverse, but it's actually not that bad. So we need to find S inverse. And since it's a 2x2, there's a shortcut, okay? And this is the only shortcut available for a 2x2. So here's a side note. Two by two, matrix A, right? If it's A, B, C, D, A inverse is equal to 1 over the determinant of A times D, A, negative B, negative C. So you flip the main diagonal and you take negatives of the off diagonal. All right, so what is that here? Well, what's the determinant of S? It's 1 plus 4, so that's 5. So in this case, right, it's 1/5 times, flip the main diagonal. That doesn't do anything because they're the same thing. And we take negatives of the off diagonal, so now this becomes a positive 1 and this becomes a negative 4. All right, and you'll realize this will work every time. Only for a 2x2, I guess. If you do this for a 3x3, we're just going to give you a 0 on the problem because you're trying to do something illegal. But okay, so now all we got to do is just multiply these matrices out. And for the sake of time, this is what happens. So if you multiply the first two matrices, you'll get 1, 24, negative 1, 6. And then you still have to multiply that by 1/5 and 1, -4, 1, 1. Okay, and then we can take the constant and we can just move it out front, right? So we don't have to deal with it right now. So now you'll get 1/5 times these two matrices multiplied, and that gets you 25, 20, 5, 10, and which is 5, 4, 1, 2. So that's the matrix that has those eigenvalues and those eigenvectors, and it wasn't that painful because we knew to use SDS inverse. So I guess this is like the other application of diagonalization that you'll see, or that you could see on the exam. Any questions? Yeah.
So, for like when you said in the beginning, like just if you were to do use brute force to go through it, like you would just try to find like one.
Yeah. Yeah, you would just guess and check. I mean, you could like, I don't even know like how painful that is to do, because like I guess like these are all positive values as well, like this final matrix. So like you could have gotten lucky at some point, and you could have used the fact that like eigenvalues add up to the trace, and the product is equal to the determinant. Right, so then you would know you need a determinant 6 matrix with a trace of 7, and then you could like guess from there. But yeah, it's not like, that's why I said if you know how to do this problem, it takes like 2 minutes to do. If you don't know how to do this problem, it'll take you like 15 minutes to do. So it's one of those problems. Any other questions? Okay, so here's another one. Number 3. Okay, this is from a 2017 midterm. All right. Here's the problem. Suppose A is 3 by 3 with eigenvalues. Lambda 1 is equal to -1, and lambda 2 is equal to lambda 3 is equal to 1. And now you have V1 is equal to 1, -1, -2. And V2 is equal to -1, 0, 1, and V3 is equal to 1, 1, 1. Okay? The first problem, the first part of the problem, A, is what is the first column of A? So this looks familiar. Okay. So there's 3 ways to do this problem, okay? The first way is to brute force an A that gets you this. All right, good luck. The second way is to do what we just did before, and so we'll go down that path. Third way, there's a shortcut. So we'll talk about that last. But so what is the first column of A? So what did we? So how do we find A? Yeah, A is SD S inverse, right? So already this one isn't as nice as the previous one because, well, you have to invert a 3 by 3, which is not the end of the world, but it's not the greatest. So you'll have 1, -1, -2, -1, 0, 1, 1, 1, 1. All right, so this is S, and then here's D, -1, -1, 1, 1 on the diagonal. Okay, so the real question comes, what is S inverse? And so here's a side calculation. So to find S inverse, we have 1, negative 1, negative 2, negative 1, 0, 1, 1, 1, 1. And then you need the identity matrix on the right-hand side. Okay, and what is this? 1, negative 1, 1, 0, negative 1, 2, 0, negative 1, 3, 1, 0, 0, 1, 1, 0, 0, 1, 1, or 1, 0, 1. All right, we'll keep reducing. 1, negative 1, 1. Let's flip this 0, 1, negative 2. So this is negative 1, 0. And then on this bottom one, we'll end up with 0, 0, 1. And then 0, negative 1, 1. Okay, and then 1, negative 1, 1, 0, 1, negative 2, 0, 0, 1. Whoa, okay, wait, not that fast. So we can make a 0 here, and we can make a 0 here. And how do we do that? Well, this is 0, negative 1, 1. All right, row 2, add 2 times row 3, negative 1, negative 3, 2. And then row 1 minus row 3, so that's 1, 1, negative 1. And then finally, 1, or 0, 1, 0, 0, 0, 1, 0, negative 1, 1, negative 1, negative 3, 2. And up here we'll get, so 1, 0, 0, add the second row, 0, negative 2, negative 1. Yeah. Is there
The first step, didn't you add 2 over 1 to row 3?
Oh no. See, this is why. Okay, so 2. All right, how does this affect anything? 2 minus, so this is a 1. And then everything here, so this is a 1. Negative 1 minus 2, 2 plus the 1, so this is a positive 1. This is a 3. This is a 1. This is a positive 1. And then we did 3 plus the bottom one, so this is 4. Does that even look right? No, that doesn't even look right. Okay, anyways, this isn't on my sheet, so this is why this method isn't the greatest, because you need to find S inverse. I apparently can't find the inverse matrices anymore. So, hold on. Let's see what happens. 2. And then you do this guy minus the top guy. So you get a 1 here. What do you do here? Is this plus 2 times the bottom row. That's fine. You do this guy plus 1. So this is a 2. This is a 3. Wait, it's this guy minus, so this is this still a 0? This is 1, 0, 0 minus the bottom row. Yeah, so this is a 0. And now you add, so that's a 1, okay. All right, did we do it? 1, 1, 1, negative 2, plus 3, plus 1, minus 1. That looks good. And then negative 1, minus 2, negative 1, minus 2. Yeah, okay, something's still wrong. It's okay. Anyways, this. Okay, so the point is, there's a clever way to do this problem. And what I didn't write down on this problem is the following. There's a hint what is v1 plus v2 plus v3? So if we go use this hint and not this crap, all right, what is that? That is 1, -1, -2, -1, 0, 1, 1, 1, 1. Or you need to add these. Okay, what do I get? I get 1, 0, 0. So how does this hint help me? All right, what is the question asking for part A? Yeah, what's the first column, right? So what's the significance of 1, 0, 0 in the first column? Yeah.
The first column has to be 0.
No. That was good guess. Yeah. Well, So not quite what I was looking for. I think it's technically correct, but that doesn't really help you in this problem. So relate what the problem's asking you to do and what we have here. Yeah, Ben.
Is it a scalar multiple of that?
Not quite. Not quite. No, okay, so the problem, right, is asking you what's the first column of A, right? What does 1, 0, 0 have to do with the first column of A? Right. What if I multiply A by 1, 0, 0? What do I get? Yeah, I get the first column of A, right? So that's what the significance of 1, 0, 0 is. So apparently, A times V1 plus V2 plus V3, right, is equal to A times 1, 0, 0. Okay? So what? Well, 1, 0, 0, we said this was the first column of A, right? A times 1, 0, 0 will get you the first column A, because the 2 zeros just kill everything else. So now we need to find what A times V1 plus V2 plus V3 is, okay? And matrix multiplication, it's distributive. So that's equal to AV1 plus AV2 plus AV3 well, what's A times V1? Yeah, it's lambda 1 times V1, right? Because V1 is an eigenvector, right? So AV1 is equal to lambda 1 V1. All right, what's A times V2? Lambda 2 times V2. All right, what's A times V3? Yeah, lambda 3 times V3. Right? This is from the definition of what it means to be an eigenvalue and an eigenvector, right? And we're given that V1, V2, V3 are eigenvectors. Or I should have written that, but it was implied. Okay, so what do we have to do now? Well, now all we do is, okay, lambda 1 was negative 1, and then we multiply that by our eigenvector. Okay, lambda 2 was 1 times V2. All right, and then lambda 3 was also 1 times V3. Yeah?
I just
Yeah, it would. It would, right? Since this isn't, since v1, v2, and v3 are a basis, right? They're an eigen, right? Because v1, v2, v3, they're literally independent eigenvectors, so they form a basis for the eigenspace, right? But together, they span a three-dimensional space, right? So that means any vector in R3 can be written in terms of these guys. And so so if you wanted to, you can extract row 2, you can extract row 3. And that's kind of what that's exactly what doing SDS inverse is doing. It's doing everything at once, because then you just get that matrix A back. So, but now we only want one column vector, we only want one vector at a time, so this makes it a little easier to do that. Okay, so this hint really helps us here, and then all we have to do is just sum these. So now this is what this ends up being -1, 2, 4. So this is really cool about eigenvalues and eigenvectors, is that I can find columns of matrices without even knowing what that matrix is, right? We don't even know what A is, we just know what the first column is. All right, any questions? Yeah.
That hint, was it given?
It was given. It was given. It was given. But even after we gave the hint, we still weren't really clear about where to go with that hint, right? And so seeing it for once like really helps. Any other questions? Yeah, Ben.
How do you know that that is the first column and not just the
Because, right, we set up here that v1 plus v2 plus v3 is equal to 1, 0, 0. Right? And then that means A times v1 plus v2 plus v3, right? Well, I can just replace v1 plus v2, v3 with 1, 0, 0, okay? And any matrix multiplying by 1, 0, 0 just extracts the first column of that matrix. Right? Got it? All right. There's a hand over here. All right. Any other questions? Okay, so the second part of this problem is also pretty applied, and it's the following. So there's a part B to this problem. Part B was what diagonal matrix does this thing have, which was like really easy to find. And then, so part C is choose all matrices that are equal to A. All right, and here are the choices. 1, A inverse. 2, A to the 2017. 3, A to the 2018. 4, A squared. And 5, our favorite multiple choice answer on every test ever. None of the above. Yeah.
Sorry, you said that the diagonal matrix is very was the second part. That was like.
Second part of the problem would just give the diagonal matrix. Will you have the eigenvalues? Yeah. It was really hard to mess that one up.
Okay.
So. Okay. How do we do this problem? All right, we can just mess around with it, right? We can just try some things first. So when you have powers, with matrices, what do you think we should do? And for those of you that were here yesterday, you should know what to do. Other people go watch that video yesterday. Yeah, Jake. Yeah, so we want to diagonalize it, right? So we have A is equal to S so S, D, and then for the sake of things, just because it's not really that important, we'll write S inverse. Right, so we have A equals SDS inverse. I couldn't find S inverse. Should be able to, but it's fine. Okay, so A equals SDS inverse, and All right. What do we need to do here? Well, okay, so what if I wanted to find a squared? What would I do?
For the diagonal.
Yeah, so remember a to any power, right? Recall a to the k is equal to s d to the k s inverse, right? I kind of did this recursive thing out yesterday where I wrote out SDS inverse a bunch of times and you just watched everything cancel, right? Except for the d's in the middle. So a to the k is SDS, a to the k is sd to the k s inverse. So a squared, right, would be s and then d squared s inverse. But this is d, so how do I square d? How do I take a diagonal matrix to a power? Yeah, you just square the diagonal entries, right? So it's squared, 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 right? So that's really s 1, 1, 1 s inverse. So is a squared equal to a? No, right? Because that middle diagonal matrix isn't the same. So okay, so we can rule out a squared. Okay, well, let's see. If we did a cubed, what would I get? I would get s, so that's d squared. I would get s and then d cubed. So now this is negative 1 cubed, 1 cubed, 1 cubed, s inverse. Well, that's equal to s negative 1, 1, 1, s inverse. Right? Is everyone okay with that, right? Because if we cube the diagonal matrix, just cube the entries. All right? So is that equal to A? Yeah, it's the exact same matrix as A, right? It's some S, right? S remains unchanged. S remains unchanged. D cubed, well, that can just end up with the same thing. And you have S inverse. Well, S inverse remains unchanged as well. So D cubed is equal to A. And we scroll up and we see d cubed isn't one of the answers, which, well, okay. But what can we notice from these two examples here? Anyone? Yeah, odd powers are the same, right? So that's because, right, we'll notice that, hey, a to the even, right, is equal to s d to the even s inverse, but evens get me 1, 1, 1. Okay? And then we notice a to the odd powers is s d to the odd s inverse. Well, that's right, s negative 1 to the odd, 1 to the odd, 1 to the odd, s inverse, and that's always going to be s negative 1, 1, 1, s inverse, and this is equal to a, right? So a to the odd is always equal to a, and therefore we can go back up here and we just choose everything with an odd power. So 1 and 2. And then after we choose those, we're done. Any questions? All right, so we've seen pretty much everything we can throw at you in terms of eigenvalues, eigenvectors for the first midterm, okay? There's really no other application I can think of because the main one we haven't really touched. I guess some problems to know for the exam. So I think, so you definitely know how to like calculate your SDS inverse, stuff like that. But there are 2 problems in the hard section, I guess 3 now, that talk about eigenvalues and eigenvectors, and they're like purely just based on like, do you know the theory, right? And if you ever get stuck well, I guess all 4 of them are theoretical. So you can see how like eigenvalues, eigenvectors, the harder problems, they're all theoretical. But if you ever get stuck on eigenvalue, eigenvector problems, and we said this in class, or I said it in class, remember that 1, the sum of the eigenvalues is equal to what? The trace of A. And the product of the eigenvalues is equal to what? The determinant of A. All right, and so now, yeah, let's talk about this. If I have matrix A, I know it's nullity. What does the nullity tell me? That's the nullity of A minus lambda I. So actually, it kind of applies here, but I just know A and I know it's nullity.
The dimension of the null space?
I know the dimension of the null space, okay? But how can I relate that to eigenvalues and eigenvectors? What am I solving? Yeah. You know the rank too, yeah. Okay. But what does the null space solve? What equation does the null space solve? X equals 0, okay? So we know the null space, right? So this is new. We know the null space of A implies AX equals 0. All right? What if I did it like this? Huh. Do we agree that the top and the bottom are the same thing? Yeah, right, because it's A minus 0I, X equals 0. Well, okay, so let's say null space of A has, so null space of A has nullity equal to some K. Okay? So nullity of K tells me the dimension of the null space. But in this case, what does it also tell me? If I write it like this. Yeah.
Assume that 0 is an eigenvalue.
Yeah, 0 is an eigenvalue, right? So we know that 0 is an eigenvalue because you can see it here, right? This is the eigenvalue equation, right? This is the eigenvalue eigenvector equation, right? So x is some eigenvector for A minus 0I, right? But I know that I know the nullity, right? So how many linearly independent x's do I have? K of them, right? The null space of A has nullity equal to K, right? That means AX equals 0 has K linearly independent eigenvectors that span it. That means down here, A minus 0I times X equals 0. That means I have K different eigenvectors for lambda equals 0. So this means that lambda equals 0 has K eigenvectors in its K linearly independent eigenvectors in its eigenspace, or spanning its eigenspace. That's a better way to say it. So for this eigenvalue, lambda equals 0, I have k linearly independent eigenvectors spanning the eigenspace of lambda equals 0. Okay? What does that also tell me? Well, if lambda equals 0 has k linearly independent eigenvectors associated with it, then how many times does lambda equals 0 appear as an eigenvalue? K times. Lambda equals 0 has multiplicity equal to k. I think you can solve number 1 on the challenging problems section now. If you use these 3 facts, I think you should be able to get number 1. Yeah.
So if you like a dumb question, but I don't understand the distinction between eigenvectors. Like if you just said vector there, would that still apply? Or no?
Yeah, it does.
Okay.
Right? It would apply because, yeah. So if we ignore the second line, right here, I would say that there are k linearly independent vectors spanning the null space.
Okay.
Right?
Yeah.
But just because I wrote A like this, right? Now this is the eigenvector equation, right? 0 is the eigenvalue, and now x's are now eigenvectors, right?
Okay.
For the specific case where lambda is equal to 0.
Okay.
So that's why I wrote that lambda equals 0 as k linearly independent eigenvectors.
Would this work if lambda isn't 0?
No. So this is literally the only case where it works. Where lambda equals 0.
So like you want to do null space of like a minus 4 lambda.
It won't work. Right? Because the reason why this works is because we can write A like this.
But can you just do like a minus 4 lambda and just call that matrix B, and that would be like the same thing? And then you have dx equals 0.
Well, but that's not a special space, right? That's the eigenspace of lambda equals 4, right? The other special thing is because since this is 0, right? Since this is A minus 0I, we essentially just had the null space, right? So I guess the other way I can phrase it is the null space of A is equal to the eigenspace for A for lambda equals 0. Right? So if you have like lambda equals 4, right? So if you have lambda equals 4, there really isn't any like special, there's nothing special, there's no special subspace corresponding to lambda equals 4. Right? It's just, all I'm trying to say is this. Null space of A is equal to the eigenspace of 1 and 0. And from that, you can deduce that lambda equals 0 has multiplicity k, and lambda equals 0 has k linearly independent eigenvalues. Any other questions? This is kind of like a mind-blowing fact, but you like after you see it for a while, it's kind of like, oh, that's like kind of obvious because A is equal to A minus 0I. Like it makes sense. But it's just the first time. You don't think of it. You're staring it in the face. You don't really think of it. So yeah, these 3 facts right here. This will help you solve number 1 on the challenging problem. Yeah.
Are these true only for non-vector?
So here's the thing. So you can't get a defective matrix that violates these things. All right, let's just think. So like the defective matrix would say the nullity is less than the multiplicity of some value, right? So the first 2 will still hold, no matter what. It's just this one, number 3. That seems like what if lambda equals 0 appeared k times, but the nullity was k minus 1, right? Because then you have this problem where the multiplicity is greater than the nullity for lambda equals 0, right? But that can't happen. Like, try to construct a matrix that does that. It's impossible. Because if you think about it, right, the dimension of the null space, like, how is it? So use the fact that the sum of the eigenvalues has to be the trace. Okay? Because then if you say, okay, so if the nullity is, so let's say I have a 3 by 3 matrix, right? And the nullity is 2, right? But I tell you that the eigenvalue appears 3 times. Well, actually, hold on. Now that I'm thinking about it, you're right. It could be violated. So there is a case, but this, let's see. So yeah, this part here is for non-defective matrices, and for example, because if you have a defective matrix, 0, 1, 0, 0, 0, 0, 0, 0, 0. This is a counterexample to what we had up there, because we can work it out, right? Lambda is equal to 0 3 times, right? Because this is a triangular matrix. So for triangular matrix, your eigenvalues are just your diagonal entries, right? And then what else? The nullity is equal to 2. Oh shoot, right? It's less than lambda equals 3. It's less than the multiplicity where the number times 0 appears. So yeah, this stuff up here you have to assume it's non-defective. Yeah.
So I just want to verify that example.
Yeah.
Position of a 1 doesn't matter so long as it's just a solitary one.
Yeah.
Okay.
Yeah, right, because all I'm saying is that, well, if the 1 was on the diagonal,
Yeah.
then the eigenvalues would be 0, 1, 0. Right? Because for a triangular matrix, the eigenvalues are just your diagonal entries.
Okay.
Right? So if the 1 were anywhere else, like here, right, then we would run into this problem again. Okay, so yeah, this is true again. So thanks Ashish for pointing this out. I got ahead of myself, but that's true if it's non-defective. So. But again, this will help you. This is the hint I'll give for for the hard problems number 1, because you'll need to use this. Okay, so why don't we take a break? Let's do 5 minutes, 8:20, and then we'll come back. We'll change gears. We'll go to linear transformations for the rest of the time.
What is trace?
Trace?
I've never seen it.
Trace is the sum of the diagonal entries.
So not the product.
Yeah, so it's just the sum of the diagonal.
I just wanted to follow up on this idea of defective matrices.
Defective is when for some eigenvalue, the nullity of the eigenspace corresponding to that eigenvalue is less than the number of times that eigenvalue. So here, 0 is 3 times. Because it's a triangular matrix, first and foremost. 0, 0, 0 is my eigenvalue. So here's 3 times. Okay? But what's the null space? Right, because you got to write for 1, right? So then for lambda equals 0, the nullity is 2.
Oh, actually, I didn't get to take advantage.
No, because you have to satisfy these two. These two conditions are always satisfied.
Yeah.
right?
Sum
So
of
the
eigenvalues
sum of the
is trace.
eigenvalues is trace, and the product of the
So
eigenvalue
it
is
has to be the
determinant.
sum, okay.
Right. So you need the sum be 0, right?
Sum has to be 0, so therefore the eigenvalues got like equal to 0, so if we can have an eigenvalue.
Right. So yeah, if you watch yesterday's video,
Yeah, I
I
think I'll
talked
go
about
over that,
I
so
talked
I'll go
about
over
this.
this.
So for like the question we talked about where you gave like the hint of these out.
Yeah.
So like if we wanted to find the second column, we would find this constant we multiply
Exactly.
by, and that would be our new like.
New thingy here. Yeah.
And so you'd be like 8 times.
What is the word?
Yeah, AC1V1 plus AC2V2 plus AC3V2.
Okay, so then you would get and then also like the definition of eigenbase is like after you plug in the lambda value. And then,
Yeah, it's the so if it's the eigenspace of the matrix, right? So there's different things. There's the eigenspace of the matrix, which is all eigenvectors you can find,
okay.
right? And then there's the eigenspace corresponding to the eigenvalue, which is all of the linear independent vectors associated with the one eigenvalue.
So like
So yeah, so if you go back, right?
these
So
ones.
here, right? So this one, right? The eigenspace, the linearly independent vectors that span the eigenspace of A are these three, whatever, the three eigenvectors that we got. This one, yeah.
So
Right.
these three. Oh, sorry. So these three form
And eigenbasis
eigenbases
for the eigenspace of A.
for the eigenspace of A.
All right.
Okay.
But this one by itself forms an eigenbasis for the eigenspace of lambda equals 3.
For this matrix.
Yeah.
So this forms an eigenbasis
Right.
for this
Right.
eigenspace.
Right.
But these three together forms an eigenbasis
Or
for this
this matrix A.
eigenspace.
Yeah.
Awesome.
So there's eigenspaces corresponding to individual lambdas, and then there's the eigenspace for the entire matrix.
Thank you.
I just want to make sure that like for as far as nullity goes, it's actually like telling you this stuff.
Yeah.
And like rank nullity, it's just telling you like how many vectors would be in the null space. So that's like what a dimension tells you basically.
Yeah, nullity just tells me how many vectors are in your basis for the null space.
That's like, is that the definition of a dimension?
Yeah, dimension is the number of elements in the basis.
Okay.
Yeah, that's
Alright. Thank you.
I don't understand what's special about the 0, because I don't understand if you just say like A minus like some number of I has nullity K, why this wouldn't work out the same way.
If I say lambda is equal to 4, there's no special subspace on A corresponding to lambda equals 4. Right, but then that's the eigenspace of lambda equals 4.
Why do we recognize that those spaces A minus some lambda I is the eigenspace of
You're saying there's nothing special about this, right? I agree with you, right? All this is just to show you that, hey, look, sometimes if you know the nullity of lambda, if you know the nullity of A, you can just tell me how many times 0 appears in the Yeah, so I talked about the nullity for lambda equals 2, right? But that's the same thing as the eigenspace. So just like A minus lambda I, you find the nullity of lambda is A minus lambda I. All right, let's continue. So I'm gonna let's just clear one thing up real quick, because it's just some terms, and then we'll move on. This will be really quick. So essentially, so let's see how to word this the best way. When I talk about the eigenspace of A, this is the space spanned by every linearly independent eigenvector of A. Okay, so the eigenspace of A is it's the space spanned by every linearly independent eigenvector of A. So in other words, it's A minus lambda I V equals 0 for every lambda. Yeah, that's what it is. Right? It's A minus lambda I equals 0 for every lambda. So it's all the eigenvectors that you find. Okay? The eigenspace of some lambda, this is the space spanned by all linearly independent eigenvectors associated with lambda. Okay, so it's when we do that case, lambda equals 1, and then we find all the eigenvectors, right? So this is the eigenspace of lambda. In other words, you can think of it as the null space of A minus lambda I. And I think I have to throw the if non-defective here. Okay? And then we have the special case, the eigenspace of 0. It's just the eigenspace of 0 is spanned by all linearly independent eigenvectors associated with 0, which means it's the null space of A minus 0I, which is equal to A, which means this is equal to the null space of A, right? And then these two, again, is non-defective. Okay. Does this make it more clear? Hopefully? Yeah.
Just go over with defective and non-defective. In one sentence.
In one sentence, if you have lambda, okay, as multiplicity, right, equal to some number n, if the null space of A minus lambda I has dimension less than n, it's defective. All right, so if null space, if this is dim less than n, then defective. All right, if it's equal to, that's fine. Move on to the next lambda. All right. So in order for the matrix to be non-defective or diagonalizable, right, every lambda needs to have multiplicity equal to the nullity. Okay. Any other questions? Yeah.
Isn't D comprised of eigenvectors of A?
D?
I mean,
D is the eigenvalue.
yeah, the eigenvalue.
Yeah. S is the eigenvalue. Okay. Hopefully, this is like the crash course in like vocabulary. All right, for eigenvalues and eigenvectors. So, okay, let's move on. Let's talk about linear transformations. So, great. Number 4 on the problem. This is from fall 2017. Okay, so it's the following. Show that P2 to R2, where T of P is equal to P prime at 5, comma P at 0, is a linear transformation. All right, do you remember how to do this? Well, so step 1 is to show that it's closed under addition, right? So we take little p1, little p2 inside p2, and now we need to see what t of p1 plus p2 is equal to. Well, that's p1 plus p2 prime at 5, comma, p1 plus p2 at 0. All right, distribute. This is now p1 prime at 5 plus p2 prime at 5, comma, p1 at 0 plus p2 at 0. And was that equal to? Anyone? Yeah, TP1 plus TP2. Okay. This should be familiar. All right, second thing, scalar mult. So we take a constant, let's call it K, in R, and then little p in P2. So now we need to say T of Kp. What is that? That's Kp prime at 5, comma, Kp prime, oh, not prime, Kp at 0, Okay, but you can just straight up just take that k out. So this is equal to k t of p. We good here? If you're confused by this, I think my recitation 6 recording, we do like 3 of these. Okay, so I guess the kind of confusing thing is like this crap right here. We'll address it in part 2 of this problem, which is find TBC with respect to the bases. B is 1x x squared, and C is E1, E2. Okay, so notice this is the standard basis, and this is also the standard basis. So there's actually no change of basis that we have to do. Okay? So now what? So now, okay, so TBC, all right, that's just telling me, hey, look, B is a basis for P2, and C is a basis for R2, and so my TBC is just, so this is dimension 2, this is dimension 3, and so I should have a 2 by 3 matrix. So what I do, so my inputs then, I need to say, okay, what's T of my B bases? So T of 1. Okay, here's the map up here, if you don't remember. T of P is equal to P prime at 5, comma, P at 0. Okay, so what do we have to do? Well, for the first entry, I should take the derivative of 1, which is 0, and I have to evaluate it at 5. But what is that? It's just 0. All right. The second entry, I take P, which is the constant function 1, and evaluate it at 0. So that's just 1. Okay? Now, next one, I do T of x. What is that equal to? Well, I take the derivative of x, which is 1, and evaluate it at 5. So I get 1. All right. And now, the second entry, I take x, right, and evaluate it at 0. So that bar with the 0 just means I'm evaluating x at 0, right? It's kind of what you do after an integral. Okay, so what is this equal to? Yeah, 1 comma 0. Okay, and lastly, here, you got t comma x squared. So, first place, I take the derivative of x squared, right, which is 2x, and evaluate it at 5. And then for the second guy, I take the I just take x squared and evaluate it at 0. So this is 10 comma 0. Okay, and then now what do I do? This is t of 1. This is t of x. This is t of x squared. and I get 0, 1, 1, 0, 10, 0. Okay. And since both were in the standard bases, I'm done. All right, there's no change of basis stuff on top of this. That's it, yeah.
Can you explain again why for T1 it's 0 and then 1? Why is it 0?
Okay, so the first entry is the first part of the map is p prime at 5, right? So you just take the derivative of 1, that's 0. Okay. The second entry is p at 0. Right, so p is just the constant function of 1. I'm evaluating it at 0. What? Because it's literally, I just literally plugged in 1. Yeah. Okay. Yeah.
So in what situation would you need to change basis?
If C was not the standard basis. Right, because this here, this is really equal to, this is really TBE. Because this basis here is standard. 1001. This is the output standard basis. Right? But since C happens to be the standard basis, then this is also equal to TBC. Right? Because C is equal to the standard basis, and E is the standard basis, right? Oh, that was a garbo. Okay? So the problem occurs when C is not equal to E. Okay? So this first step here, right, I just plugged in the basis of B in here, right? And evaluated, I got some outputs. But these outputs are all in terms of the standard basis. Okay? And so that's why then, so I just put it in the matrix here. Right? So this is really TBE, but since C, right, is obviously the standard basis as well, then we're just automatically done. Right? If C were not the standard basis, then I would need to find change of basis matrix from what to what? Not, you got it backwards, right? Because this output is an E, right? And I need to end up at C. So I need to find change of basis from E to C. So in this case, right, if we wanted to do it, right, we would find P E to C. Here's C, here's E. All right, what do I put in C? 1001, right? Because it's just the standard basis. That's what C is. Okay? And what do I put in E? Yeah, 1001, because E is the standard basis as well, right? So we're done, right? Since the left-hand side is the identity matrix already, so then this would be your change of basis matrix. And then you'd multiply it out in front, right? TBC is equal to PEC times TBE, but that's just the identity matrix times 0, 1, 1, 0, 10, 0. Right? So there's no point in doing any of this, right? When you have the standard bases. Hold some hands, yeah.
If, I don't know if it would ever not say, but if it didn't give us like a C, you just assume it's.
Yeah, if you don't see anything, you just assume standard.
Even like for a polynomial, it's just 1x.
Exactly, yeah, always. If it doesn't say anything, just assume the standard basis.
What about for a matrix?
You just unravel it.
What would, if it didn't say, M2 is just, yeah.
No, it's the 1, 0, 0, 0.
Yeah.
0, 1, 0, 0. 0, 0, 1, 0.
Oh,
0, 0,
okay.
0, 1. Yeah.
And then you just said, like, if you have a 2 by 2 matrix, it's
I would check out my recitation video on bases. I go over the standard bases in that one. Yeah.
Does the fact that B was a standard basis change the problem at all?
No, because even if B were not a standard basis, I would just plug in those random B guys into these red circles here. Right? So this is like a general, like, cover all type of method. It's just that when you have C is the standard basis, you're just done after plugging it in. So. Okay. Everyone good with this? Yeah? 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 Okay. All right. These are just, these few are pretty plug and chug. 5, this is from spring 2018. All right, you got V is equal to P2R. B is equal to 2 plus x squared, 1 plus x, 2x plus x squared. C is equal to 1 plus x squared, x plus x squared, 1 plus x. That better be right. Yeah, it is. Okay. B. Okay, so I gave you the 2 bases. And the question is literally just find P, B, C. All right, and just to hammer this home, when you see this kind of notation, always just think, all right, this is really P, B, 2C, because then it makes setting up this matrix really simple. All right, so what we do is we take the basis of C, and we take these guys and we throw them in here, and then we take the basis of B and we throw them in here. And so what we get is we get 1, 1, 1, 0, 1, 1, 1, 1, 0. Right, so again, I'm assuming 1x, x squared. And then over here, I get 2, 0, 1, 1, 1, 0, 0, 2, 1. Okay, what do we want? Yeah, identity on the left-hand side. So this is just an exercise then in row reducing. Okay, so this I actually have written down on my sheet, so there will not be mistakes. So this is 1, 0, 1. All right, so the first row stays the same. We're just going to zero out these guys right here. 0, 1, 0, negative 2, 0, 2, 0, 1, negative 1, negative 1, negative 1, 1. Reduce. 1, 0, 1, 0, 1, 0, 0, 0, negative 1. So I got rid of that bottom. I got rid of this guy. 2, 1, 0, negative 2, 0, 2, negative 1, negative 1, 1. And then from here, we can just get to the identity matrix kind of simply. So now we got 1, 0, 0, 0, 1, 0, 0, 0, 1. And we get 3, 0, 1, negative 2, 0, 2, negative 1, 1, 1. And so this thing is P, B, C. Okay. Yeah?
When doesn't this work?
It will always work. Yeah, as long as you set the things up in the right order. That's why I encourage you to write it this way, because it's almost impossible to get it mixed up then when you have it written like that. So, yeah.
If you write line of x squared as columns instead of rows, does that also work?
Ooh. Yes. But your inputs would be weird. No, because then you can't have column vectors as your inputs. Right? Because your column vectors assume this Yeah, just put stuff into columns. That's always a good rule of thumb. Okay, let's take a look at another one. It's about the same as the one we saw yesterday. Spring 2015 midterm. Consider W the subspace of M 2×2R, and really could have just wrote M2R, but okay. Consisting of all matrices such that A11 equals 2A12 and A22 is equal to 3A2. Okay, part A is just like show something, show this basis is a basis for the subspace. We're not going to do that. Part B is find the change of basis matrix PBC, where C is equal to 2, 1, 1, 3, comma 6, 3, 2, 1, and B is equal to 2, 1, 0, 0, comma 0, 0, 1, 3. Okay, so again, just more standard stuff. So here we go. We put C here and we put B here. 2, 1, 1, 3, 6, 3, 2, 1. That doesn't look right. This is a 6. All right, so it's 6, 3, 2, 6, not 6, 3, 2, 1. All right, on the right-hand side, we got 2, 0, 1, 0, 0, 1, 0, 3. Okay, so what did I say yesterday about the change of basis matrix? It has to be square, right? Because change of basis matrix happens within the same vector space, right? So it can't have weird dimensions. It must be square. Well, if we reduce this thing, it's not going to be square. So what can we do? Okay, so if you get rid of the first and last row, why can we do that?
Because they're the scalar multiple of the second row.
Yeah, so this first row is a scalar multiple of the second row, and this last row is a scalar multiple of the third row, right? So we can essentially just kill them for the change of basis matrix exercise, because we need a square matrix. All right, so now we got 1, 3, 1, 0, 1, 2, 0, 1. And we just go on from here. 1, 3, 0, negative 1, 1, 0, negative 1, 1. 1, 0, so I'm adding 3 times the bottom, negative 2, 3, 0, and then I'll just flip the signs. All right, any questions? This is like the problem we did yesterday. Yeah, Jake? Part A shows a base. I don't remember which one of these it said was the basis for the subspace. So it's just, right, how do we show something's a basis? What are 2 conditions?
Oh,
Span linearly independent. Right? That's for basis. So, or you can use the theorem if you know the dimension of the subspace. Right? You only need to find the number of linearly independent vectors that are equal to the dimension of the subspace. Then they'll span, and then they'll be a basis. Okay, we good? Okay. So finally, let's do 7. So for 2015 midterm. This is the last one. Let 0, 1, 1, 0, 1, 0, 3, 0, 0, 2, 2, 0, 1, 0, 3, 0, 0, 1, 1, 1, 2t, t squared, negative 5, 2. That's your matrix. I'll give you guys some time to copy that down. Okay, so that's your matrix. Part A. It's find T such that rank A is equal to nullity A. All right, B for T is equal to negative 1. Find a basis for Colspace A. Okay. Let's do part A. Now, how do you do part A? Any ideas? Yeah.
We'll reduce above and then solve for or find t that makes rank equal to 2.
Rank equal to 2. So first of all, what does rank have to be to equal nullity? 3. Right? Because rank nullity theorem says that rank plus nullity equals. Right. So rank nullity theorem says rank plus nullity equals dumb columns. So in this case, it's equal to 6, right? And then for rank and nullity to be the same, we want 3 plus 3. Okay, so essentially we want this matrix to have rank 3. Okay. So now we need a row reduce. So let's just say I already wrote that matrix down again. What can we do? Well, we have some, it looks like we have some repeated columns, right? So I can just like ignore this column since it's the same thing as this guy, right? And I'll ignore that column as well because it's just a scalar multiple of this matrix. So really, we can just find this thing. Okay, reduce. We'll do 1, 0, 1. So we'll switch the first and second. Rows. Okay, so we switch the first 2 rows. And now we want to zero out the first column. So this becomes 0, 3, 0. And this is negative 5 minus t squared. 0, 0, 1, 2. All right, continue to reduce. So now we want to zero out this entry. So now we got 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1. And this is t squared 2t. This is negative 5 minus t squared minus 3 times 2t. So minus 6t. And then this is a 2. Okay, so what's true about this that makes makes us have rank 3? Yeah, so we need this polynomial here to be 0. So we need this equals 0. And so let's write it where we can actually recognize it as a polynomial. And so that's negative t squared minus 6t minus 5. You want this to be 0. Factor out a negative sign. So you got negative times the quantity t squared plus 6 plus 5 is 0. Factor that inside quantity, negative t plus 5 t plus 1 equals 0, and you see that t is equal to negative 1 and negative 5. And so that solves part A. Yeah?
Can you go over again why you could cross out the column?
Yeah, so I'll let people copy this if they're still copying. But essentially, what's going to happen is that since these columns are equal, are like, because we're trying to find rank, right? And how do we find rank? Well, one way we can find rank, finding rank, we look at the number of pivots in the columns, right? That's one way we can find rank. And, well, if you have repeated columns, or like scalar multiple columns, they're obviously not going to have a pivot in them. Do you see why or no? So here's the way to think about it, all right? Rank is equal to the dimension of the column space, right? And what is the definition of the column space? Right, but what's the definition of the column space? It's the span of all of the linearly independent columns. Right? So if we have obviously not linearly independent columns, they're not going to be in the column space. Right? Since they're dependent on something else, right? So the column space, we only want the linearly independent columns. And the dimension of the column space is equal to the rank. Right? So that's why we can just drop these linearly dependent columns, because they're not going to contribute to the column space, so they won't contribute to the rank. Okay? So now what do we need to do for part B is for t equals negative 1, find a basis for column space A. Well, if you plug in t equals negative 1, well, you can just plug it in here, right? And what do we get? We get that this row is 0. Right? So for part B, we just see that we get some matrix that looks like 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, t squared. So now you plug in negative 1. You get 1, negative 2, 0, 2. Pivot, pivot, pivot. Free? But these aren't the columns of my column space. My column space is equal to the span of these 3 columns that have a pivot in them. So that's going to be this one, and that one, which is 0, 1, 1, 0, comma, 1, 0, 3, 0, comma, 0, 1, 1, 1. And so that's the column space of A. Any questions? Okay, so I'm out of questions. So I think we're done here. I guess it's 9 o'clock, so that's nice. So, all right. This is going to be uploaded tonight. There's a wealth of stuff. You have this review session. You got yesterday's review session. You got all the practice problems. The way I would study for this exam is, first of all, get that homework out of the way as quick as you can, because those are just mechanics. Okay? It's just mechanics on how to do these problems. You really want to know, I told this yesterday, but from the 2 review sessions plus the practice problems, you're going to see 6 of the 7 problems on the midterm. And then the last one is just some definitions that you'll need to know. So that's pretty much it. That's the midterm. So get used to the practice problems. Rewatch these at like 5 times speed, whatever YouTube allows you to do them at. And yeah, I'll see you guys then next time. And for those of you in Friday recitation for me, feel free to show up on Wednesday because we're going to be going over cheat sheet stuff on Friday.
So just the last thing was I did over here span that were originally the ones that later would have to put on pivots. Yeah. Okay. The second thing I have was in the linear system. So like this big sort of matrix we got over here.
Linear transformation.
This like this was so then we like we kind of enter like these values into it and then like kind of what's this representing and multiply this by this. We're going to look here by this here.
So this just represents a transformation that if you have some vector expressed in terms of v,
yeah,
this will get you the output in terms of c.
Okay, interesting. So that's just like thank you very much.
A to the negative 1 because a to the negative 1 is just you take the diagonal. It's s d to the negative 1 s inverse, right? So you're taking the diagonal entries and you're raising them to the negative 1, right? But this is still negative 1. This is 1 and this is 1, so it's the same thing. So any odd power works there. Yeah. So negative 1 technically is odd, sure. Yeah. So that's why it works there.
Also for the first one, but does it matter what order we put these vectors in?
No, but it matters that this column corresponds to the 3, right? Because 0, 1, 0 you found with lambda equals 3. So if 3 is in your first column, then this has to be in the first column.
Lastly, for this problem where we found out that the addition if we wanted to extract like 0, 1, 0, could we make, for example, if 2v plus v2?
Yeah, then you would just say a times 2v1 minus 7v2 plus 4v3 is equal to 0, 1, 0.
And we would do the same thing.
And you would do the same thing, except you would have that additional scalar in here, like 2, negative 7, 4, like what I said. Yeah. Okay.
Are you responsible for
No.
None of these?
No. Not, oh wait, hold on. Kernel, invertible, range, and composition. No, I don't think so. No, there's one on the homework that's like invertibility one, but that's just like, that one's just, it's just to show that this is a linear transformation that happens to use an inverse map. Right, that's all it is. You don't actually have to like know what the inverse map is. Although it's just, if you have a matrix of transformation that's square, and if you can invert it, that's the inverse map. So it makes intuitive sense what it's supposed to be, but you don't have to know it. So, yeah.
So I have like a couple of questions. So
Okay. Sure.
I just want to, you said you're doing stand up on Wednesday.
Wednesday, yeah.
When is your? I have Friday.
It's on my website. Yeah. Everything you want to know about me is on my
So it's
website.
cool. I can show up if I want to.
Yeah, I think so. I don't think it's not going to be taking classes this week, especially if you're on Friday.
Yeah.
Right, because we're going to cancel my investigations.
I was just wondering, why do we have a rotation this week when we're not doing new material?
Oh, well, I mean, yeah, I'm going to cover cheat sheet stuff. So
Right, but other than that, they are just canceled.
we will probably cancel, we will likely cancel
And you guys will email us.
Yeah.
Okay, cool. Appreciate it, man. Thank you.
Yes.
No, you have homework.
Oh, homework? Okay. Which ones do you want? Or
Like a whole lot.
I only have 5 or 4 that are relevant.
Okay.
So
Those then.
right, yeah, these are by the second one, the piles are sorted. So so you're just gonna have to tell me when you see it.
Okay.
Oh, God, we got all this stuff on.
I probably won't.
Yes, you
You have it.
What?
There you
Yeah,
go.
there you go. Yep.
Will Zelda also have hands-off recitations on Wednesday?
Yeah, I think so.
Are you guys doing the same thing?
Yeah, I don't, because I'm like pretty experienced in dealing with these recitations before midterm, so like I know what I'm gonna cover. I don't like, we usually try to coordinate it, but I only send them like rough like lessons, outline sketches of like recitations, not the entire thing, because like a lot of things I like do the morning of recitation. So yeah, he'll have like a general idea of what I'm talking about, but I don't know. It's gonna be recorded and all that stuff. Like I record all my recitations, so Wednesday 9 a.m. will be recorded. So I mean, I guess if you want to show up, you can. What?
Yours is at 9?
No, I have 8 and 9.
Okay.
Right. So all the times are listed on my website.
Okay.
So everything is there, all the resources. So, yeah.
Cool. Okay, cool. So.
Okay, wait. Let me turn this off since we're
Yeah,
right by the
for
mic.
sure.
Unless you want to record this in case you want to listen to this later.
No, it's not
Okay.
a big deal.
Okay.
Is everybody gonna listen to everything?
Wait.
That's so funny.
No, I don't. I think people drop out like once I'm done.
They're young, so stupid. That's funny. We're going to